Our old friend, well-known Marian Marinov from Bulgaria. And please give him another great applause because he has so many problems reaching Zagreb yesterday, but he is here now. So thank you very much for coming here. He will talk about fault tolerance services.
Okay. So I'm famous for, last year was it, Linus wrote to me, fuck no, in an email. So this year I decided not to talk about stuff with famous people in Linux. I decided to talk about high available systems. So how many of you run websites? Any website? How many of you run a service that your boss says should run 24/7, 365 the whole year? And how many of you have had to stay up late or wake up early to fix this system that doesn't work, website or whatever? This hopefully will help you. It will not solve your problems, but it will reduce them. This is the main idea. Highly available systems. I have been working with Corosync and Pacemaker since maybe 2006, and before that I was talking about Heartbeat, which is the first implementation that did have availability in Linux. So I have my fair share of problems with these things. I want to start with this schema here. You have 3 servers here, and first you have to know that Corosync is the messaging layer between them. In Heartbeat, before that, we had one system that was doing both the messaging and decision-making for what should run, what shouldn't, and so on. With separation of Corosync and Pacemaker into 2 completely different softwares, we actually get more for less. With Corosync, we can check if all the servers in our cluster are up, if we need to add another server, we simply need to talk to Corosync. We can check the status of all of these servers. And then on the local node, on the physical server, you run additional software that takes your configuration and applies it to the services that you're running. This means that in this case, you have Pacemaker running on all servers, checking everything for you. And the combination is the highly available setup. You can run Corosync without Pacemaker, but without Pacemaker, you cannot do all the fancy stuff that you can do with it. Pacemaker adds the resource management. You have a project on GitHub that is only the resource scripts, nothing else. A resource is your service. So, for example, you have an Apache web server, it's a resource. You have a MySQL that you want to be covered by master-slave replication, no problem, it's another resource. Usually, when you configure Corosync and Pacemaker, you get to read the docs, you read a lot of XML, it's hard to understand, it's very easy to break. It's strange. So the Pacemaker developers created this very nice shell that is called CRM, Cluster Resource Manager, and it worked for years. I think 3 or 4 years back, they decided to make another one called PCM, Pacemaker Configuration System. I'm not used to PCS. I prefer CRM. So what you see here is only CRM configuration. So the easiest cluster you usually would configure with Corosync and Pacemaker, and I'm not talking about installation, I'm talking after you have installed Corosync and Pacemaker, you have all of your servers visible in your Corosync, then you need to add these 4 lines here. You define the nodes that usually Corosync gives you out of the box, so you don't need to. And then you have these 2 lines. The first line defines the Apache resource. And there you see LSB column Apache, and I'll talk a bit later about this. Then you have another primitive called IP. In this case, we have this IP 122, so on, assigned to bond 0. Now, what Corosync and Pacemaker together does is, if, for example, Jerry dies and this IP 122 was living, actually running on Jerry, it would be moved on Tom. So you would have a little bit of downtime, but it's a little bit, less than a second usually, of downtime. And also, with these two lines, Pacemaker will make sure that you have Apache running somewhere. Unfortunately, this is not a very good configuration because since Apache is not running on all of your servers, both on Tom and Jerry, you may end up in a situation where your IP is on Tom and your Apache web server is running on Jerry. So now you have to decide how to work with this. And usually what I'm doing is I'm creating from this resource Apache, I'm creating a clone. A clone is another type of resource that is supposed to run on multiple machines, and you can configure it differently. So the other thing that I'm adding here is something that I really advise you to do for web servers. Bind your web servers on local IPs. And if you can't, on all of the IPs on port 80. In my case, on most of the systems we run, we cannot run the web servers on all of the interfaces because some of the IPs should be dedicated, for example, for engines or varnish or whatever. So run it on local IPs and add destination NATs to there. So when the IP is actually moved on your machine and you have Apache running, you don't need to restart Apache. You simply need to get the traffic to there, which you're doing with the DNAT. So a little bit more complex. I'm focusing only on configuration. If you don't understand anything, just stop me. I have prepared a lot of other configuration for you to explain. For these 30 minutes, I want to explain only configs. So we have this nice cluster of 3 nodes here. We have, again, Apache. We have bind. We have cron migrate. Cron migrate is a shell script that, for example, I wrote, which acts as a normal init script. So here, first, op monitor interval 2 seconds. This means that Pacemaker will issue etc initd Apache status every 2 seconds. It would do the same for bind, but named, and it would be on interval 5 seconds. So if the service is down for, the service can be down for 5 seconds, and after that, Pacemaker would know and will react to this. So we have another thing for cron migrate. I have set it to 15 seconds. And here on cron migrate, we also have another meta tag is managed. You can stop Pacemaker from monitoring your services, and only for one resource or for the whole machine. First, you can see the standby flag on the nodes. You can put a node on standby, so it won't apply any changes that Pacemaker thinks that needs to be done. And also, you can, with this managed meta flag, you can actually change this for each resource. This allows you, for example, in my case, sometimes I have to stop Apache for an upgrade from one machine or another machine. It's easier for me to simply put it in unmanaged mode, and in this case, Pacemaker would not check it. I can move the IPs to the other machines where I have running Apaches, and then restart the Apache, check everything if it is working, and then put it again in managed mode. We have also 2 IPs, and this is not the whole config. It's freeze white. So we have a clone service here for the bind and for the Apache. keep in mind that we have also cron migrate script, which is not here, which means that cron migrate will run only on a single machine. Out of these three, it will run only on a single machine. When the service, for some reason, dies on this server or doesn't work, simply the status is returned with error, then Corosync Pacemaker will detect this, and Corosync will relay a message to the other machines that one of those machines should run this service. So cron migrate will be started on another machine. Here, for the Apache, you can see that it says clone max 3. This means that if I have more than 3 machines on the cluster, Apache will run only on 3 of those. And you're not specifying which are those 3. It simply says we need 3. The other thing is on a single physical machine, you can actually make a service to run more than one time. Like, for example, you can have a service that needs at least 2 or 3 instances on the local machine, and oh, sorry. Sorry for that. So you can have a service that really needs at least 2 or 3 nodes or instances running on each node. You can configure this with clone node max. With clone node max 1, this means that this service can run only a single instance on one server. This is very nice for most of the services. I haven't used it with more than one, but I have friends that actually have done this. And the other is, should it start in order? Order equals false. You can configure which service should start first, then second, then third, and so on. This is very important in some cases, like, for example, you may want your MySQL service to start first to be running before you actually move the IP to this service. Because if you move the IP before the service is up, actually you will get network traffic that will see errors because your service is still starting. You may start both the IP and MySQL in the same time, but you know that MySQL with large databases start for considerable time. So in this case, you would get a lot of errors. And you can order what needs to be started and finished starting before actually other services are started. Okay. The last thing here is location constraints. There are some things that you may want to get together. Like we have here a co-location constraint. Don't put the cron with the web nodes. This means that I simply don't want the cron service to be running where the IP10 and IP10 and IP11 are. This is important for me because the crons are CPU and IO intensive, and they may break the web nodes. So I have more nodes in my cluster, and I can allow one of these nodes to be only for the cron. Also, I can tell the cron service where I want it to run generally. So the location constraint here tells cron migrate to run on CLUC. CLUC is one of the 3 nodes that we defined in the beginning, like here, the first node. So it will run there, and here it says infinity CLUC. This means that I really prefer the cron to stay on this machine and not to go on any other machine. If this machine dies, the machine is dead, you cannot run cron there. And if you have another machine which is not running, which does not run IP10 and IP11, it's very simple for you to move the cron. In our 3-node cluster, the cron would not start anywhere because the other 2 IPs would be on Han and Leia. The last thing here, most of these come as defaults when you set up your cluster, but there are a few that you need to know about. It's tolerant, which is shoot the other node in the head. Very nice feature of highly available systems. In this case, is disabled. In most cases, when you have one service, cluster for one service, you want to be sure that the other node will not come back with like, for example, if you have MySQL replication and you have master-slave replication, master died, you have promoted the slave to master state, the slave just makes sure that the master is really dead by sending an IPMI shutdown command to the other machine, so it powers it down. It must be sure that there are no other masters running. This is one of the features of shoot the other node in the head. You have different scripts that you can use for shooting the other node. You can use SSH, you can use IPMI, you can use other APIs. Default option here is managed. The first time you put your cluster into unmanaged mode, the whole cluster, this option shows up here. And it's set to false, then you can simply set it to true. You have the maintenance mode. Maintenance mode is actually when your cluster is not working anymore. Like, you may want to reboot one of the machines, but you don't want this to affect anything on your cluster, so you manually add the location constraints to move your IPs, your services, to the other machines that won't be rebooted, and then you put your cluster software, the Pacemaker, in unmanaged mode. This means that it would never check any of the services anymore, and then after you restart the machine, you put it in managed mode again. This should work automatically, but should is not every time. So when we are doing maintenance, I prefer to have this. The last thing is an option that you actually need when you have a cluster of 2 machines. And everyone who have read something about clusters and highly available setups knows that 2 machines is a very bad idea, extremely bad idea, because if the connection between them is broken, for example, if this is a MySQL replication again, and the connection is broken, you may end up with 2 masters working, and one of the web servers seeing one of the masters, and 2 or 3 of your web servers seeing the other master. And this is called split brain. And usually when you have more machines, you can simply have, you rely on quorum that you get from Corosync. Corosync sees that here you have 2 machines and here you have 3 machines. Okay, this means that these 3 machines actually have quorum, they are more than the others, and on them you run the MySQL master. The others would shut down the service. But if you don't have the machines, usually, this is what happens, is you want to build a cluster with at least 2 machines, right? So if one machine dies, the other should work to replace it or to take the resources from it. I have a load balancer config that I can show you if you want, that actually does this. And the last thing here, resource stickiness. If a service have run on Leia and Leia dies, the Pacemaker software will see that Leia died and will simply move the service to another working machine, right? But when Leia comes back, Pacemaker knows that Leia is back, and it will move the service back to it. Usually this is nice, but sometimes these moves from one machine to another machine, if you have a flapping network or something like this, can actually create downtime, because every time you restart your service, it stops working for some time. So resource stickiness gives additional score to the service, to each resource, so it can stay on the machine that it has been moved. So it would never go back to the first machine from where it was moved. It's a good feature, but it works only for certain services. You have the clone service, you have master-slave service. Clone is very nice, but if you want to have replication for PostgreSQL, for MySQL, or for Redis, for example, you need to have the knowledge of who is the master and who is the slave. This is very important for you, because you cannot run two masters, right? So you have different resource type that is called master-slave. You have the Linux standard-based scripts. This is your standard init scripts. You can write an init script that does start, stop, restart, and status, and that's it. It would be possible to add this as a resource to your cluster configuration. The others are open cluster framework. OCF scripts are a little bit more complex. They have an API behind them. The idea is that you export different variables from Pacemaker before you start this actual script, and you get other information from the OCF script. So you cannot write a master-slave resource with LSB. It has to be an OCF script, because the LSBs do not export the information about who is the master, who is the slave. Additional information like MySQL, for example, gives you which is the current walk file, the walk position, and so on. Redis gives you information about is it in sync, and so on. So you can do this with writing these scripts. They're located over here, and on the GitHub repo, you can download any of the scripts and simply write your own OCF script. It takes like 100 more lines than an init script, so it's not very complex. Another thing that Pacemaker can do for you is the ordering. I told you, you can define which service is started after which. And here I actually would want to show you another configuration that I have prepared. Where was it? Okay, here. So when we are demoting and promoting a DB node, we simply want to make sure that first the IP has stopped, and then we will demote the MySQL. When promoting, we must make sure first that the MySQL is promoted, so it's not read-only anymore, and then we'll have the IP moved to this machine. This is important because if you first move the IP and then make the MySQL writable, promote it to master actually, you would get a lot of errors from MySQL queries that try to write something. So this is the most basic ordering that you want to add. And nothing is basic with highly available systems. And with Pacemaker, it's, it's really hard to make it work very well. Location constraints and ordering are the two things that are very, very hard to do right, because as you have seen with the cron, here we have two location constraints that actually contradict when the machine that we want to run the cron doesn't work. Simply because the second constraint will not allow us to run this service. And if it is vital for our company, it should run somewhere, right? So making this right is a little bit complex. You can define this, the first location constraint. Instead, with infinity, you can add -100. -100 tells that this is a score that you add to the service. So it tells that it should not run anywhere else except, what was it, CLUC. But if CLUC dies, I don't have any preference. I can run it anywhere else. That's possible. We cannot have this scoring mechanism with the co-location constraint, which says, okay, don't run cron migrate here. So easy, because if machine dies, here if we have set infinity, it will never run there. But with minus 100, if everything is calculated right, and there is a paper of around 50 pages that explains how co-location is calculated, you would get cron service running on one of the machines that are actually running IP10 or IP11. So first one is contradicting the second one simply because it says infinity. If it also said minus 100, you would actually be able to migrate, cron migrate to one of the other machines. Okay. And that's it. I have nothing for questions, sorry. But if somebody has question, I'm here until 12 o'clock, so you can find me and ask questions.
Any questions?
I have time for questions. Nice. Nobody wants to run this in their production environment? This is the de facto standard for highly available systems, right?
Marian, I'll break the ice again. Okay, which cluster is the best for this? Database or
which cluster? You can run whatever. I have load balancers with engines that are running with Corosync and Pacemaker. I have database clusters. I have other web services. I have APIs highly available with this. So whatever. There's another question there. If you can define a script for starting, restarting, and status of this, it is suitable for Corosync and Pacemaker.
Hi. So how would you compare its reliability to previous Heartbeat 2 and Heartbeat 1?
How I can compare Heartbeat with this? Okay, Heartbeat suffers from a lot of problems. You cannot define the co-location and location constraints with Heartbeat. Heartbeat still works. I still have a cluster that runs Heartbeat since 2003. So it works if you don't upgrade anything. But with Pacemaker, you can have more advanced configuration logic that you cannot encode in Heartbeat. Also, since Corosync is separated from the logic, you can have different ways of communicating. Like Corosync allows you to have multiple channels for communicating, while Heartbeat allows you a single channel. You configure it either unicast or multicast, and that's it. And with Corosync, you can have on this device, on this network, I want to have it multicast. On this network, I want it unicast. On this network, additional network, I can get different results.
Can you make it communicate to the storage area network? So it can like...
can you run Corosync on the storage?
Yeah, but because like we had a problem with in the Heartbeat days, you had like 2 different locations and redundant servers on them. And when you had network flopping, it would either break in a split brain way because you didn't have Stoneit, or if you did have Stoneit, then it simply died and your service didn't run at all because one side decided, okay, I cannot get a call.
I understand you very well. So if you can run Corosync on that, that's not a problem. Usually the first example that you get in the documentation is using Corosync and Pacemaker to configure DRBD, Distributed Replicated Block Device. And you know, there are exactly the same problems there. So the Limbit guys wrote a very nice OCF script that can handle most of these things. And also with Pacemaker, you have a resource called ping, and you can define this resource and use it as additional score for your services. So, for example, if both of the servers can ping the gateway, okay, they are up. They may be not able to communicate between each other, but if they can both communicate to the gateway, they are up. You can configure stuff like this, and you can add additional checks like this with Pacemaker, which were impossible with Heartbeat.
Okay, thank you.
More questions? Oh.
So basically this is the standard way of doing high availability, and I think it's the best way. But have you tried to use some auto-discovery daemons like etc daemon or console, because they can also do leader election on different level basically?
I haven't tried auto-discovery because I simply know how it works, so it's a lot slower. But I have tried VRRPD, which is the virtual router redundancy protocol, right? And you have VRRPD and Keep Alive D that are the two implementations of the protocol on Linux. And with them, you can do master-slave fault tolerance. But unfortunately, you don't have all the OCF scripts, so you have to write everything by yourself. And also the other problem is that they work only by master-slave, so only the master gets all the resources and the slave doesn't get anything. When, for example, you have a load balancer, you would want all of your traffic to go, and you have two machines, you would want all of your traffic to go to both of the load balancers. So, for example, this is the output of CRM in the CRM shell, and this is a configuration for a load balancer. You simply define two IPs as a DNS record for your website, and you run Apache on all of the servers. In this case, you run Nginx on all of the servers. And actually, here, Pacemaker detected that there is a problem with Nginx running on one of the load balancers. And you can use the resources of both machines, and you can define what happens if one of the machines dies. That's it. That's so simple there.
But yeah, but basically you can do the same thing with etc daemon or console. It can also do.
Yes, you can do it with etcd. You can do it with snarf. The problem is that it's a lot faster this way. First of all, and second, you have all the tested scripts, and this is very, very extremely important to have a tested script. I was the first to introduce the MySQL OCF script there. We are still patching this script to this day for like 5 years now, and it still doesn't work flawlessly on every setup. So if we have devoted 5 years of development of a single script and it still doesn't work, do you think that you can do it? And by we, I'm talking about the community around Pacemaker. Do you think that you can, by yourself, do it, make it work correctly 100% of the time? This is the problem that you get. This is a standard, and there is a big community around it, and you have the support around it. If you go on vacation, do you really want to be the one that get called because of a problem with this? If there is a community, your guys in the office can still help you. They can go and ask the community without you.
Yeah, you're correct, but sometimes you cannot use this. Because I don't know, you don't have you cannot deploy load balancer on the same subnet, or it's on different DC, and it's much more complicated doing this way.
If you cannot have two machines on the same subnet, it's not called cluster.
Okay.
Dobrica? More questions? No? Thank you very much for trying so hard to arrive on time.